Okay, so we will start the session. Hello, hi, namaskar. I'm Prashil. I'm a Prime Minister's Research Fellow at IIT Mumbai, and here we are learning advanced thermodynamics and molecular simulations. So this is our last interaction session where we'll be talking about the summary of the entire classes that we had in last 2 to 3 months, right? And then we'll be solving some of the questions from one of the assignments. So these questions will be helpful for you while giving exam, right? So in these subjects, what we learned. So the subject was meant to be there for performing computer simulations. Performing computer simulations. So what do we need to perform simulations? Simulations are basically computer based experiments, right? So if you want to do any experiments, you need something, right? What you need? For example, if I want to check what is the solubility of sugar in water. If I want to do this experiment, then what I need? I need one beaker, right? Then I would need water, and third thing is sugar. I will keep on adding sugar here in the water, and I'll stir the solution. Continuous stirring, right? What will happen eventually? This sugar amount, I'll keep on adding and I'll keep on dissolving the sugar. After a certain time, what will happen? Sugar will stop dissolve. Sugar will not dissolve beyond certain amount. Beyond certain amount, the sugar will not dissolve, right? And that's where we'll calculate, okay, if I'm taking this much of, for example, 100 ml water, then what is the maximum that sugar that I can add? For example, 20 gram example, right? So the solubility will be 20 gram per 100 gram, right? So this is what is 0.2 gram per water gram water, right? This is how we do the simulations, correct? Now how to do the same thing on computer? Because what you had seen here, we need this much things to perform a simple experiment, right? Simple experiment, not complex, right? So we need some material, so it is costly. So what would I say? It requires some amount, right? It requires expenditure some expenditure is need to be put in, right? Some amount, some rupees we have to add to purchase these things. If you want to analyze in more detail how sugar molecules are distributed, what do you need? We need to perform again some of high cost. We need to use some of the high cost instrumentation, which is not the case in computer experiment, which is not the case in computer experiment, right? What do we need in computer simulations? Let me know. Can one of you tell me? We do not need any equipment, we just need one computer, right? And that is available with everyone, right? Available with everyone, correct? So to do these simulations, what do we need? We need just one computer. What else we need? What else we need? So to do these computer experiments, we have to learn first of all the theory, how to simulate, how to simulate, or how to perform computer simulations. So there is a theory, and that theory is given as statistical mechanics. Just like what we do, we'll consider one box, and in that box there will be some particles. They will be keep on moving, right? Inside the box only, right? They will keep on moving, and then we'll just apply some principles. For example, total energy is equals to is what? Total energy is equals to kinetic energy plus potential energy. Use these principles, use differential equations, or I would rather say mathematics. Then you model what is happening, right? Model the system. Once you model the system, once you model the system, once you model the system, you will get some equation. That an equation solve using again numerical method, right? Correct. What else we need? Just a minute. This is how we need these things, right? So to solve or to perform the computer simulation, we have to understand, okay, what is the theory, and using that principle we got some equations. That's what we did in our first part. And then using that we'll get some equation. That equation we need to solve. What else you get? What else you need to put in? Right? What else is needed? Just like in the case of ideal gas, what we obtained. Again, how did we get this equation? Using modeling non-interacting gas. So we assume that, okay, gas particles are there in a box and they are not interacting, they are far apart from each other. We got this equation, right? What was the next stage? What was the next stage? In the next stage, what did we do? We consider that all the particles are not non-interacting, right? So they actually interact. So this is some model that they took, where they are saying if molecule, this one atom is here, other atom is here, these are not interacting at any distance, they will not interact. Even if it is close, it will not interact, right? So this is how the assumptions they took. But that assumption may or may not work, right? That assumption may or may not work. Therefore there were some improvements, and because of which we got to know, okay, that if there is interaction between particles and we are considering that particles do not penetrate, then there will be new case, and based on that we designed or devised or modeled other equation of states, right? What were those equations? For example, I am telling you van der Waals equation of state, right? So what it has actually is, it has some parameters, right, which we need to substitute. So for example, what is my temperature, what is my pressure? Then if there is a gas, for that gas I'll be having some diameter of the particle that we need to substitute. If the gas is not spherical, then there will be some arrangement will be there. For example, this is ellipsoidal, right? So ellipsoidal, that means there will be some sphericity factor will be there, that sphericity factor that we add and get the properties of that. So what is actually there in the equation? In that equation we need, which we need to solve, we need to add some parameters. We need to so provide the values of some parameters to get the things, to get the properties for your system, right? And yes, same equation we solve using methods, for example molecular dynamics or Monte Carlo simulations. In these simulations we do the same. We have some equations that we solve, right? That we solve, these equations we solve, correct? And these are nothing but solution methods. So the theory is same, theory is same, only the thing that is changing is solution method. Ultimately what is our aim? Our aim is to get the properties. Our aim is to find the properties, and that should match experiment. For example, this experiments that I had told you, right? Solubility of sugar in water. So what we did just now, we added some chemical in water, and then we wanted to see what is the maximum capacity of that chemical in capacity in water, right? Now the question is, if I want to do same experiment at different temperature, what do I need to do? What do I need to do? Tell me. So our ultimate aim is to solve some equation such that we will get some results, and those results we got without doing any experimentation. That means our experimental results or our simulations results should match with the experiment. So what we do in that case, Just like I had given you example, in beaker I'm adding sugar, correct? And I'm seeing what is the maximum capacity. So I will do computer simulation. That means I will solve mathematical equation, right? And I'll get some property. So for example, I got, okay, zero point 0.2 gram per gram water can go, zero point 0.2 gram of sugar can go in 1 gram of water, example, right? I'll verify that with this. Compare these two. We will have to compare these two. If this is matching, that means our simulations are correct. If matching with certain level of accuracy, right? If it is matching, that means our simulations are correct. And now I don't need to do any experiment further. If I want to do it at temperature T1, T2, T3, and so on, in that case I will just perform simulation because I have matched this case. Verified first simulation, no need other experiments. And validation, we don't need to do any validation now because one thing we have matched, so we will assume that okay, these things will also match. Our simulations are correct, that means we are getting the results, and hence we will not do any experiments beyond, right? So we will be just doing the simulation. This is how we study, right? So we have to replace the we have to replace the experimental cost, right? We have to replace the experiments with the simulations. We have to help experimental team to save time and money, right? That's where we have to do this thing. Now with this background we will be solving the questions. So question number 1 is on your screen. Please try to solve. About Monte Carlo simulation. So what is Monte Carlo simulation? What is Monte Carlo simulation? And it is asking what is not true. What is not true? What is Monte Carlo simulations? Tell me. So what is Monte Carlo simulations? We have a system. For example, I have a box. In this box I have some molecules, and these molecules could be any gas or solid or liquid state. It can be in gas, liquid or solid, either of these states. What I do in this, I take one particle, I move that particle. So before moving the particle, I know what is my interaction energy potential between particles. So for example, ULJ 4 epsilon 12. Right, so I know the distance between each of the pairs, and based on that distance, if I know what is the diameter of that gas and what is the polarizability, right, this is what is experimentally available. I'll calculate what is interaction energy, right, and calculate the interaction energy. That is U, and then perform displacement or any other move. Example, I am just doing NVT, that is what is, for example, it is in canonical ensemble. For this canonical ensemble, perform displacement move. That means I am randomly picking that particle and moving it at some distance. Random displacement. U2. What is the change in energy? Then we have to calculate delta U, which is U2 minus U1. U2 minus U1. Right? That means what has happened? Initially, this particle was here. We'll calculate its interaction energy with the rest of the particle. We'll calculate what is the interaction energy of the same particle at certain distance when there is a displacement of that particle, right? And then we'll get what is change in the energy. If the change in energy is negative, then that move is accepted. If it is positive, then move may accept it, right, depending on the energy. If energy is too high, rejection of that move, the chances of rejection of that move is high. Energy is too high, then chances of rejections are higher. So depending on the delta U, the probability might look like this. This is my zero distance. See, if the energy is negative, Okay, the energy is negative, probability, right? And if it is positive, as the delta U value increases, the probability becomes lesser and lesser. That means accepting this move has a lesser probability. Correct, and this probability is delta U divided by kb t. So for this particular canonical ensemble where the temperature is only the factor, we just compare with thermal energy, right? And then we calculate whether that move is accepted or not, right? So in this simulation we just did displacement. Similarly, we can exchange the volume. We can perform grand canonical Monte Carlo simulation also. What does this mean? This in grand canonical simulations we have mu, v, and t. So if the chemical potential is constant, number of molecules can be added into the system and can be removed from the system. So there is change in the number of molecules, right? At equilibrium, U value will be constant and the net change is equals to 0. Volume is constant, that means pressure can fluctuate. Temperature is constant, that means energy can fluctuate, right? So barostat we can use for pressure control. Volume change moves can also be performed, and simulation can be performed in grand canonical ensemble. But yes, as I told you, this is my probability which is in canonical ensemble, may not be necessarily true for grand canonical Monte Carlo simulation, that is GCMC. So in that case, Metropolis acceptance criteria will be different. So what is not true? Not true is this: Metropolis acceptance criteria is same. It is saying same in all ensemble, which is not the case. It is different, and that's why that is a statement which is false. Correct. Then there is question number 2 on your screen. Question number 2. Just like what we studied in previous question, tell me the answer for this. How are we controlling the temperature? How are we controlling the temperature? Just like what we discussed in question number 1, what is the answer for question 2? See, the probability of acceptance is P, right? Which is given as delta U divided by kBT, which will tell you whether that move is accepted or not. For example, just like here, if I displace a particle, there will be corresponding energy change. that is delta U, and that delta U is normalized by kBT. So here that temperature is coming, right? So the temperature factor is here. That means temperature control is achieved in one control simulation using Metropolis criteria of accepting the trial modes. We don't use any thermostat just like what we did in molecular dynamics MD simulation. There, what we follow is we calculate the velocity in each step, and that velocity is then related to kinetic energy. That means half kBT is equals to half mv square, half mv square, right? So this is the way we did in MD, but in case of Monte Carlo, that is not the case. It is through the Metropolis criteria of acceptance. So answer to this question is option 4. Option 4. Right? Option 4 is the answer. Right? Then there is question number 3, which is on your screen. Grand Canonical Monte Carlo simulations does not involve following move. What is Grand Canonical Monte Carlo simulation? First of all, we need to understand what is Grand Canonical ensemble. Right, ensemble. So this is what is mu vt, we studied, right? Mu vt. So if mu is constant, that means number of molecules are changing. So I have a system where molecule can add and go out, right? So mass transfer is there. Mass transfer is there, right? Then volume is constant, that means pressure is changing, right? Pressure is changing, so volume change is not allowed. So this is wrong. What is not true? So what is not true? Volume change is accepted. This is not true. But then what happens? I have particles in the system. Those can move from one location to other, right? All particles have been given a freedom to move from one location to other. That's where particle displacement is happening. As I said, particle addition deletion is also happening. Particle removal included. Volume change is not accepted. And once all these things are changing, the three that are marked correct, energy will automatically change. That means temperature is constant. Temperature is constant. So Grand Canonical Monte Carlo simulation does not involve volume change. So option this is correct. Right? Option number 4. Reservoir is explicitly simulated. So just like I had said, what is Grand Canonical ensemble? Similarly, there is Gibbs ensemble Monte Carlo simulation that tells you mu pt, which is mu pt, and this mu pt will reservoir is explicitly simulated in Gibbs ensemble. Gibbs ensemble, right? This reservoir is explicitly simulated, so we have reservoir. Similarly, in Grand Canonical Monte Carlo also we have a reservoir which has water molecules or any other chemical with which system is exchanging the particles. So this is also correct. Canonical, we have temperature control, but explicit Reservoir is mostly modern gives. Thermodynamic integration is required. Why do we need thermodynamic integration? It is a method, right? Just like in the start of the lecture, what I said, we have a theory and we have multiple methods to solve the equation. So one of the method is thermodynamic integration. So thermodynamic integration is used to calculate the free energy difference. Free energy difference, right? This is what we studied, right? Then chemical potential can be written as a function of canonical partition function of this and this. So we will have to write n plus 1 divided by n, right? We take their ratio and that is equals to the chemical potential, right? This is what is the answer to this question. This is also again thermodynamic integration method. I think it's thermodynamic cycle. Thermodynamic cycle is there, right? Yes, thermodynamic cycle. So what we do, we have for example drug, right? Only drug. I have to solve it this drug. So drug and in its surrounding we have some water. So what I do, I have drug, red one, then I have water, then there is drug plus water, and this is also loop. So we will be knowing okay what is the delta G for each step, and then we just sum it. Delta G overall is equals to delta G1 plus delta G2 and so on, right? So multiple steps are involved and that forms a thermodynamic cycle. This thermodynamic cycle can be used to compute the binding free energies, right? Binding free energy, solution free energy if it is water, if there is a drug and then there is a uh, receptor, right? So in that case it is also called as drug binding, receptor binding free energies, right? So this is how it is. So do let me know if there are any doubts. I am here. Will be so. The next question, that is last question of the day, right? So last question of the day is metadynamics. Metadynamics is an enhanced sampling method. For example, if there is a particle and I am asking that particle to move, right? So it can move because this is an empty box. But if there is some thick liquid that is present inside which I want this atom to move, then there are restrictions and there are chances that it may trap in some zone which we call as a local minimum. So energy landscape will look like this. So what has happened, earlier particle was somewhere here and it has trapped over here, but the global minima is here. Ultimately it wants to go here, but then it is trapped. So now how to get this particle out of it? So we have to fill some sand over here, we have to provide some extra energy over here, and whatever is the magnitude of the extra energy we have provided will give you the barrier height. This is the energy required to get it out, right? So this is an enhanced sampling method to get to the global minima, and it has been used to explore the free energy landscape. It has been used to explore the free energy landscape. So this is how metadynamics is used. It is an advanced sampling method which can be used, right, in the simulation. That's all for the today's session. If there are any doubts, you can reach out to me, and if there are no doubts, we can mm, close the session, right? So thank you guys for connecting. Have a good day.